Hi. The first topic in the chemistry syllabus for Common University Entrance Test is solid state. Some of you may not have studied solid state in class 12, but you need not worry. I am uploading video classes on the prescribed topics in 3 parts, which includes a lot of previous year multiple choice questions and other model questions for CUET UG. By the way, I am Dr. Sariq Matthew, a retired professor in chemistry. The purpose of my channel, Chemistry Master, is to upload video classes on topics in chemistry related to NEET, JEE Main and Advanced, CUET, and other similar examinations. If you like the video, please subscribe my channel and forward to others. In Solid State Part 3, we study about imperfections in solids and the electrical and magnetic properties of solids. By solids, we mean crystalline solids. As seen earlier, in crystalline solids, the constant particles are close-packed, leaving minimum vacant space. We can observe perfectly ordered arrangement of constant particles in crystalline solids. Any deviation from perfectly ordered arrangement of particles in a crystal give rise to crystal defect or imperfections. For simplicity of explanation, the constant particles in a solid are assumed to be hard spheres, which generates a three-dimensional structure. Ideally, a crystal consists of a perfectly periodic array of atoms or ions. However, deviations may occur. The term imperfection or defect is used to describe any deviation from such orderly array. Broadly speaking, there are two types of defects in crystals: point defects and line defects. Point defects are the irregularities or deviation from ideal arrangement around a point or an atom in a crystalline substance. And this is a perfectly ordered arrangement. Suppose one constant is missing, it gives a defect. So this defect is around this point. One atom is missing from its location. On the other hand, a line defect is arise due to the irregularities or deviation from ideal arrangement in entire rows of lattice points. So if you take this row, the constants are arranged in an ideal manner. But in the second row, there are gaps between the constants. A dislocation in the arrangement of row occur in this case. Crystal defects can be classified in this way. So, point defects and line defects. We need to study point defects only. Point defects are further classified into stoichiometric defect, impurity defects, and non-stoichiometric defects. Stoichiometric defects are further classified into vacancy defect, interstitial defect, fungal defect, and a Shorty defect. Now, the non-stoichiometric defects are of two types: metal excess defect and a metal deficiency defect. First, let us consider stoichiometric defects. The stoichiometric defects are point defects that do not disturb the stoichiometry of the compound, also known as intrinsic or thermodynamic defects. Basically, there are two types: the vacancy defects and the interstitial defects. When constituents of the crystals are ions, these defects are called Shorty defect and fungal defects. First, vacancy defect. The vacancy defect decreases the density of the substance. Also occur when a substance is heated. This is a perfectly ordered crystal. Suppose that a constituent is missing. So if one constituent is missing, another also should be missing. And this creates a vacancy. Suppose the crystal is AB type. If one A vacancy occurs, there should be another B vacancy. So the stoichiometry of the compound is not affected. The second defect is interstitial defect. It increases the density of the crystal. So this is a perfectly ordered arrangement. Now an extra atom is in the interstices. So if there is an A atom in the interstices, there should be another B atom also. And so that the stoichiometry remains the same. Shorty defect is a stoichiometric vacancy defect that occurs when the constants are ions. The number of missing cation and anions are equal. Say a perfectly ordered crystal lattice of positive and negative ions. Suppose a cation is missing and an anion also is missing. The number of missing cations and anions are equal to maintain the electrical neutrality. In sodium chloride, there are about 10 raised to 6 Shorty pairs per centimeter cube of crystal at room temperature. If we take 1 centimeter cube in sodium chloride, there will be 10 raised to 6 pairs. Pairs means positive and negative ions. The defect decreases the density of the solid because of the vacancies. And such defects are mainly shown by ionic solids in which the size of cation and anion are almost similar and have high coordination number. Examples of compounds that show such defect is sodium chloride, potassium chloride, cesium chloride, potassium bromide, silver bromide, etc. Next is Frankel defect. Frankel defect is a stoichiometric interstitial defect. And that also is shown by ionic solid. So this is a perfectly ordered ionic crystal and one cation is slipping into the interstices. And usually cation goes to the interstices because cations are smaller. It does not change the density of the solid, shown by ionic substances where there is larger difference in the size of the ions. Stability of the crystal decreases, but the conductivity increases. Examples are zinc sulfate, silver chloride, silver bromide, silver iodide, etc. Silver bromide exhibits both type of defects, Shorty defect as well as Frankel defect. The second category is impurity defect. Impurity defects in crystal occurs when a foreign atom or ion different from the host atom are present in the crystal lattice, either substituting for or occupying interstitial positions. As for example, sodium chloride, and one of the sodium atom is replaced by a strontium ion. The defects discussed so far do not disturb the stoichiometry of the crystalline substances. Now let us consider non-stoichiometric defects. Those defects in crystals which leads to a change in composition of solids are called non-stoichiometric defects. They contain constant elements in non-stoichiometric ratio due to defects in their crystal structure. An example is ferrous oxide with a 0.93 iron and a nickel oxide with a 0.94 nickel. These are of two types, metal excess defect and metal deficiency defect. Metal excess defects are of two types, metal excess due to anionic vacancies and metal excess due to extra cation. Consider the sodium chloride crystal. When sodium chloride crystals are heated in an atmosphere of sodium vapor, the sodium atoms get deposited on the surface of the crystal. Chloride ions now migrate to the surface of the crystal and combine with sodium to form sodium chloride. Now the electron released from sodium diffuse into the crystal and occupy the anionic site. So these are the sodium that is deposited on the surface and a chloride ion migrate to the surface forms sodium chloride. Now the electron released from the sodium atom occupy the vacancy produced by the chloride ion. These sites are called epicenters, and epicenters are responsible for the color of the crystal. Electron in the epicenter can absorb visible light and get excited. For sodium chloride, the color will be yellow. Excess of lithium makes lithium chloride crystal pink, and excess of potassium makes potassium chloride crystal violet or lilac. The metal excess defect due to extra cation. So a perfectly ordered arrangement. Now a cation is present in the interstices. And in order to compensate the charge, an electron also occupy an interstitial position. So the crystal as a whole is neutral. An example is when zinc oxide is heated, oxygen is released and a zinc 2 plus and 2 electrons are produced. The excess zinc ions now move into the interstitial sites and electrons to the neighboring interstitial sites. Because of excess of zinc ions, the formula becomes zinc 1 plus XO. Zinc oxide is white in color at room temperature but turns yellow on heating. So this is because this electron can absorb energy from the radiation and it can move to higher energy levels. Next is metal deficiency defect. There are many solids which are difficult to prepare in stoichiometric composition and contains less amount of metal as compared to the stoichiometric proportion. A typical example is ferrous oxide. Ferrous oxide is mostly found in the composition Fe 0.950. Fe may vary from 0.93 to 0.96. So a perfectly ordered arrangement. And this defect arises due to the missing of a cation from its lattice site and the presence of a cation of higher charge in the neighboring lattice site, so that the crystal as a whole is neutral. This defect occurs when the metal shows variable valency. An example is transition metal compounds such as ferrous oxide, ferrous sulfide, nickel oxide, etc. shows such defect. Ferrous oxide is mostly found in the composition Fe 0.950. In crystals of ferrous oxide, some Fe2 plus cations are missing and the loss of positive charge is made up by the presence of required number of Fe3 plus ions. Such defects are usually shown by metals which exhibit variable valencies. Solids can be classified into three types based on the electrical conductivity: conductors, insulators, and semiconductors. A metallic conductor conducts electricity through the movement of electrons, and an electrolyte conducts electricity by the movement of ions. In conductors, conductivities range between 10 raised to 4 to 10 raised to 7 reciprocal ohm per meter or Siemens per meter. Reciprocal ohm is Siemens, which is the SI unit of electrical conductance. Insulators show very low conductivities ranging between 10 raised to minus 20 to 10 raised to minus 10 reciprocal ohm per meter or Siemens per meter. In semiconductors, the conductivities are in the intermediate range from 10 raised to minus 6 to 10 raised to 4 reciprocal ohm per meter. The conductivity of metals depend upon the number of valence electrons available per atom. Metals conduct electricity in solid as well as in molten state. An oversimplified theory of metals which could explain some of its properties is the electron sea model. A solid metal is considered as a network of positive ions immersed in a sea or pool of electrons. These are valence electrons and are not attached to any particular ion and can move freely. If electrons from an external source enter a metal wire at one end, free electrons pass through the wire and leave the other end at the same rate. In this way, electrical conductivity is explained. The lustrous appearance of metal could be explained as due to absorption of visible light by these electrons. The electron C model is a simple qualitative description of metallic state, but for most purposes we use the band theory of metallic bonding, which is a form of molecular orbital theory. In metals, the molecular orbital formed from atomic orbitals are very close in energy to each other. This forms an energy band. The energy band in which valence electrons are present is called valence band. If valence band is partially filled and the energy difference between occupied and unoccupied levels is small, electrons can move from filled level to unfilled level by the application of a small potential across the crystal. For example, the 2s band of lithium. Such bands are called conduction bands. 2s band of lithium is both a valence band and a conduction band. Conduction band can occur in another way also. In addition to valence band, there may be vacant bands which are having higher energy. If the valence band is filled and overlaps with a higher energy vacant band, electrons can easily flow into these bands, forming conduction band. For example, beryllium has a filled 2s valence band, but the empty 2p band is very close in energy and overlaps with the valence band. The lowest levels of 2p band are at a lower level than the highest levels of 2s band. In semiconductors, the valence and conduction bands are separated by small energy gap. For insulators, there is large energy difference between valence band and conduction band. The energy gap is usually called forbidden gap. Combination of valence and conduction bands depend on the structure and symmetry of crystal lattice. We can explain the band theory by taking two simple metals, lithium and beryllium. Lithium has a 2s atomic orbitals and it contains only one electron. Now imagine the formation of molecular orbitals between two lithium atoms. Each lithium atom contributes one 2s atomic orbital, leading to the formation of two molecular orbitals, sigma 2s and sigma star 2s. Since the total number of electrons is 2, both the electrons occupy the sigma 2s molecular orbit and the sigma star 2s molecular orbital is empty. Now consider 3 lithium atoms, and 3 lithium atoms give 3 molecular orbitals, and again half of it will be empty. In this way, imagine the formation of molecular orbitals between n lithium atoms. There will be n molecular orbitals. As the number of molecular orbital increases, the energy gap between the molecular orbital decreases and the energy levels appears to be a band. This band is known as the energy band. For lithium, half of it will be filled, half will be empty. These electrons are responsible for bonding the lithium atoms together. These are valence electrons, and the band in which they are found is called valence band. Because the energy difference between the occupied and unoccupied level in the valence band is so small, electrons can be easily excited from the highest filled level to the lowest unfilled level. We can represent this band in a simple way. And this represents the filled level and this is the empty level. So here the 2s level is completely filled and here it is empty. Because the energy difference between the occupied and unoccupied levels in the valence band are so small, electron can be easily excited from the highest filled level to the lowest unfilled level that lie immediately above the filled level. This can be accomplished by applying a small electric potential difference across the crystal. And this is how the band theory explains the ability of metal to conduct electricity. Such partially filled bands are called conduction bands. The 2s band in lithium is both valence band as well as conduction band. But in the case of beryllium, the 2s orbital has 2 electrons and hence the 2s band is filled, but the 2p band is vacant. Here, the 2p vacant band overlap with the filled 2s band. The lowest level of 2p band, that is red, is lower than the highest level of the 2s band. So valence electron can move to the empty molecular orbital. And such bands are called conduction bands. Band theory can be used to distinguish between, say, metal semiconductors and insulators. So for metals, the valence band may be partially filled. That is for in the case of lithium or sodium. So electrons can be excited from the filled portion to the empty portion, and thus we can expect conductivity. In the case of certain other metals like beryllium, the valence band is completely filled, but the conduction band is vacant, but both overlap. So electrons can be easily excited from the valence band to the conduction band. This is the case with metals, either partially filled valence band or empty conduction band overlap with the valence band. In the case of semiconductors, the valence band is completely filled and the conduction band is empty, and the difference between the valence band and the conduction band is very small. So therefore electrons can be easily excited from the valence band to the conduction band. That shows a limited amount of conductivity. But in the case of insulators, the valence band is filled but the conduction band empty. There is a large energy difference between the valence band and the conduction band, and there is no way to transfer electrons from the valence band to the conduction band. Thus the material behaves as an insulator. Intrinsic semiconductors. For semiconductors, the gap between valence band and the conduction band is small. Hence, some electrons may jump to the conduction band and show some conductivity. Increase in temperature will increase such conductivity as more electrons can jump to conduction band at a higher temperature. Silicon and germanium show this type of behavior and are called intrinsic semiconductors. The conductivity of intrinsic semiconductors is too low to be of practical use. The conductivity can be increased by adding an appropriate amount of suitable impurity. This process is called doping. Doping can be done with an impurity which is electron rich or electron deficient as compared to the intrinsic semiconductor, silicon or germanium. Such semiconductors are called extrinsic semiconductors. When silicon or germanium is doped with some impurities, we get extrinsic semiconductors. And one type is electron-rich impurities. Silicon is having 4 valency electrons, and it combines with the other silicon to form the silicon crystal. So this is the perfect silicon crystal. Now imagine that one of the silicon atom is replaced by an electron-rich atom such as phosphorus or arsenic, which belong to group 15. So silicon and germanium group 14, but phosphorus or arsenic are group 15. Now for arsenic there will be 5 valence electrons, and out of that 4 will be used to form bond with the neighboring silicon atoms, and the 5th one is labile. These delocalized electrons increase the conductivity of the doped silicon or germanium. Hence silicon or germanium doped with the electron-rich impurity is called N-type semiconductors. Silicon and germanium can also be doped with electron-deficient impurities. A perfectly ordered crystal of silicon. Now we replace one of the silicon atom by a boron atom. And a boron belongs to group 13. And the boron has only 3 valence electrons. So therefore, one valence electron is missing. The place where the fourth valence electron is missing is called a hole or electron vacancy. An electron from a neighboring atom can come and fill the electron hole. In doing so, it will leave an electron hole at its original position. When this happens, it would appear as if the electron hole has moved in the direction opposite to that of the electron that filled the hole. So it appears to be the electron hole is moving in this direction, but the electron is moving in the opposite direction. Under the influence of an electric field, the electrons would move towards the positively charged plate through electron holes, but it would appear as if the electron holes are positively charged and are moving towards the negatively charged plates. This type of semiconductors is called p-type semiconductors. This figure shows an n-type semiconductor. It contains an excess of electrons. There may also some holes also may be present. And this is the p-type semiconductor. There are electron holes. There may be a few electrons also. Here we apply a positive charge, here negative, here positive, and here negative. If we apply the charge, the electrons will move towards the positive pole, and that is the case with the n-type semiconductors. But in the case of p-type semiconductors, the holes appear to move towards the negative electron. And this is the case with the p-type semiconductors. Many electronic components are made by various combinations of n-type and p-type semiconductors. Diode is a combination of n-type and p-type semiconductor, and it is used as a rectifier. Transistors are made by sandwiching one type of semiconductor between two layers of other type of semiconductor. That is, NPN or PNP type of transistors are used to detect or amplify radio or audio signals. Solar cell is an efficient photodiode used for converting light energy into electrical energy. These are some rectifiers and diodes. Germanium and silicon are group 14 elements, and therefore they have a characteristic valency of 4 and forms 4 bonds. Combination of elements which simulates an average valency of 4 are found to possess characteristic properties. A large variety of solid-state materials have been prepared by combination of group 13 and group 15 or group 12 and group 16 to simulate average valence of 4 as in germanium or silicon. For example, that is an element from group 13 and an element from group 15. So the valency of group 13 element is 3 and that of group 15 is 5. So the average valence will be 5 plus 3, 8 by 2 is 4. And they are called 13-15 compounds. And examples are gallium arsenide, indium antimonide, aluminum phosphide, gallium nitride, etc. Gallium arsenide is known for its high electron mobility and a suitable band gap, and it has revolutionized the design of semiconductor devices. Another class is 12-16, and this is group 12, and this one is group 16, and the valence of group 12 is 2 and 16 is 6. So 6 plus 2, 8, average is equal to 4. And examples are cadmium sulfide, cadmium selenide, mercury telluride. These are examples of such metals which show semiconductor characteristics. Some transition metal oxides such as titanium oxide, chromium dioxide, rhenium oxide behave like metals. Some other oxides like vanadium oxide, vanadium dioxide, vanadium trioxide, titanium trioxide, etc. to show metallic or insulating properties depending on temperature. Every substance has some magnetic properties associated with it. These properties are due to the electrons present. Each electron in an atom behaves like a tiny magnet. Its magnetic moment originates from two types of motions, orbital motion and the spin motion. Electron being a charged particle and undergoing these motions can be considered as a small loop of current which generates magnetic moment. The magnitude of this magnetic moment is very small and is measured in the unit called Bohr magneton. One Bohr magneton is 9.27 into 10 raised to minus 24 ampere meter square or joule per Tesla. Consider a spatial orbital, for example, a 1s orbital. Now I am placing an electron here. Imagine that the electron is spinning in the anti-clockwise direction. Spin motion, and it generates the spin magnetic moment. Or we say that a spinning electron behaves like a tiny bar magnet. Now the second motion is the orbital motion. And this orbital motion also generates a magnetic moment, which we call as the orbital magnetic moment. In both the cases, angular momentums are there, spin angular momentum and orbital angular momentum. We know if two electrons are associated with the same spatial orbital, their spin must be opposite. So suppose I am placing a second electron in the same spatial orbital, its spin should be opposite from that of this one. This electron also is spinning and it generates a magnetic moment. And the second electron also behaves like a tiny bar magnet, but the direction of the magnetic moment will be opposite. And here we say the spin is up or a spin up, and this one we call it as spin down. So when electrons are paired, their spin magnetic moments also get cancelled. You should remember one more thing, animations never represent the real situation. The purpose is to give you an idea of the concept. On the basis of magnetic properties, substances can be classified into 5 categories: paramagnetic, diamagnetic, ferromagnetic, antiferromagnetic, and ferrimagnetic. Paramagnetic substances are those substances which are weakly attracted by the magnetic field. They are magnetized in the same direction as that of the magnetic field and lose magnetism in the absence of field. They have one or more unpaired electrons. Examples: oxygen, Cu2 plus, Fe3 plus, chromium 3 plus, titanium oxide, etc. Diamagnetic substances are weakly repelled by the magnetic field. They are weakly magnetized in a magnetic field in the opposite direction. All electrons are paired. Pairing of electrons cancels their magnetic moment. Example: water, sodium chloride, ethane, vanadium pentoxide, etc. Ferromagnetic substances are strongly attracted to the magnetic field. They can be permanently magnetized. Metal ions are grouped to form domains, and the domains orient in the same direction as that of the magnetic field. The ordering of domains persists even when the magnetic field is removed and become permanent magnet. In an unmagnetized piece of ferromagnetic substance, the domains are randomly oriented and their magnetic moment get cancelled. Examples of such paramagnetic substances are iron, cobalt, nickel, gadolinium, chromium oxide, etc. Antiferromagnetic substances form domains like ferromagnetic substances, but no net magnetic moment as the domains orient in opposite direction in the magnetic field. Examples are manganese oxide, manganese dioxide, Mn2O, nickel oxide, etc. In ferrimagnetic substances, magnetic moments of domains are arranged in parallel and anti-parallel direction in unequal numbers, weakly attracted to the magnetic field compared to ferromagnetic substances. Examples are magnetite ferrites like MgFe2O4, zinc Fe2O4, etc. Ferrimagnetic substances lose magnetism on heating and become paramagnetic. This is an example of a paramagnetic substance. The spins are randomly oriented. If you apply a magnetic field, the spin orient in the same direction as the applied field and become a magnet. If you remove the magnetic field, the spins again become randomly oriented and lose magnetism. And this is ferromagnetic substance. These are the domains. Each domain acts as a tiny bar magnet, but they are randomly oriented, so there is no net magnetic field. When placed in an external magnetic field, the domains orient in the same direction. Even if we remove the magnetic field, the orientation remains the same. And that is why these substances are used for the preparation of permanent magnets. In the case of antiferromagnetic substances, the domains orient in the opposite direction and they lose magnetic moment, or the magnetic field get cancelled. For the ferrimagnetic substances, within the domain, the spins are arranged parallel as well as anti-parallel ways, but there will be some spins that orient along the applied field, so they show slight magnetic field. But when it is heated, the arrangement is dislocated and become paramagnetic. Now let us work out some multiple choice questions from part 3, that is imperfections in solids and electrical and magnetic properties. Question 1. Which kind of defect is observed in silver bromide? 1. Vacancy defect, 2. Interstitial defect, 3. Both fungal and shorty defect, only shorty defect. Silver bromide shows both fungal and shorty defects. The radius ratio of silver bromide is intermediate, hence it shows both fungal and shorty defects. Shorty defect arises when both silver plus and Br minus ions are absent from their lattice sites. They have comparable sizes. Because of the high mobility of Ag plus ions, they easily move to the interstitial sites, leading to fungal defect. Question 2. The shorty defect may involve all but one of the following statements. The incorrect statement is 1. Vacant cation is to anion site in the ratio 1:2 in mx2 lattice. A vacant cation and a vacant anion in an mx lattice. Vacant cation is to anion sites in the ratio 2:1 in an m2x lattice. For random vacancy in any lattice. Shorty defect cannot have random vacancy. So this is the answer. Shorty defect will not disturb the stoichiometry of the solid. If random vacancy occurs, it will not maintain the electrical neutrality of the crystal. Question 3. The shorty defect is shown by 1. Strongly ionic compounds, 2. Compounds having high coordination number, 3. Compounds containing cations and anions of almost similar size, all these. Shorty defect is shown by all these type of compounds. So that is the correct answer. Question 4. Which of the following defects are shown by KCl crystal? A. Shorty defect, B. Fungal defect, C. Metal excess defect, D. Metal deficiency defect. Option 1. A and B only, A and C only, B and C only, B and D only. Since the size of K plus and Cl minus are comparable, KCl shows shorty defect. Potassium chloride, when heated in an atmosphere of potassium vapor, chloride ions migrate to the surface of the crystal, creating anion vacancies, leading to the formation of F centers. And this creates metal excess defect. Therefore, potassium chloride shows Shorty defect and metal excess defect. Question 5. What type of crystal defect is indicated in the diagram below? 1. Frankel defect, Shorty defect, then Frankel and Shorty defects. So this vacancy is for the positive ion, this vacancy is for the negative ion, this is for positive, and this one is for negative. So equal number of cations and anions are missing. So the answer should be Shorty defect. Question 6. The appearance of color in solid alkali metal halides is generally due to 1. Shorty defect, 2. Frankel defect, 3. Interstitial defect, and 4. F centers. The color is due to F centers. In solid alkali metal halides, the color is due to the presence of F center, which is found as a defect in the crystal structure. Anionic sites are occupied by electrons. Question 7. Cations are dislocated into interstitial sites in option 1. Shorty defect, Frankel defect, metal deficiency defect, vacancy defect. The smaller ion, usually cation, is dislocated from its normal site to interstitial site in Frankel defect. So answer is Frankel defect. Question 8. The incorrect statement about imperfections in solid is 1. Shorty defect decreases the density of the substance. 2. Interstitial defect decreases the density of the substance. 3. Frankel defect does not alter the density of the substance. 4. Vacancy defect increases the density of the substance. So we have to choose the incorrect statement. Here the incorrect statement is fourth one. Vacancy defect increases the density. Vacancy defect decreases the density. When some of the lattice sites are vacant, the crystal is said to have vacancy defect. This will decrease the density of the substance. Question 9. Zinc oxide is white in color at room temperature. It appears yellow on heating because of option 1. Frankel defect, Shorty defect, metal excess defect, or metal deficiency defect. We have learned that when metal oxide is heated, it loses oxygen, and this leads to metal excess defect. Zinc oxide, when heated, oxygen is released and zinc 2 plus and 2 electrons are produced. These excess zinc ions move to the interstitial sites and electron to the neighboring interstitial sites. So these are the electrons in the interstitial site, and this is the zinc ion in the interstitial site. So therefore there is an excess of positive charge that causes a metal excess defect. Question 10. Nickel oxide on analysis showed the molecular formula as nickel 0.98 What percentage of nickel is present as nickel ions? Option 1 96%, option 2 4%, option 3 98%, option 4 2%. So we have to do some calculations to find the answer. The formula of the nickel oxide is given as nickel 0.98 and oxygen 1. If we take 100 nickel oxide molecule, it will contain 98 nickel ions and 100 oxide ions. Nickel must be present as nickel 2 plus and nickel 3 plus. And let the number of nickel 2 plus ions be X. Therefore, the number of nickel 3 plus ions will be 98 minus X if we take 100 nickel oxide. The nickel oxide molecules must be neutral. That is, nickel 2 plus nickel 3 plus O2 minus should be equal to 0. Number of nickel 2 plus ion is taken as x. Nickel 2 plus is plus 2 charge. So plus 2 into x. Nickel 3 plus is 98 minus x. So it is plus 3 into 98 minus x plus oxygen is minus 2. Minus 2 into 100 should be 0. So from this we arrive at the value of x as 94. That is, nickel 2 plus is 94. Therefore nickel 3 plus must be 98 minus 94 equal to 4. Therefore percentage of nickel 3 plus will be 4 by 98. 98 is the total number of nickel atoms. And after that 4 is nickel 3 plus. So it is 4.08 or approximately 4%. Therefore the correct option is second option. Question 11. Which of the following statements about the interstitial compounds is incorrect? 1. They are chemically reactive. They are much harder than pure metal. They have high melting point than pure metal. They retain metallic conductivity. In interstitial compounds, small atoms like hydrogen, boron and carbon enter into the void sites of the metal lattice. They retain metallic conductivity and are chemically inert. Option 1 is the correct answer. Question 12. It is an assertion reason question. Given below are two statements. One is labeled as assertion A and the other as reason R. Assertion. In a particular point defect, an ionic solid is electrically neutral even if few of its cations are missing from its unit cells. And a reason. In an ionic solid, frontal defect arises due to dislocation of cation from its lattice site to interstitial site, maintaining overall electrical neutrality. In the light of above statements, choose the most appropriate answer from the options given below. Option 1, A is not correct, but R is correct. Option 2, both A and R are correct, and R is the correct explanation of A. Both A and R are correct, and R is not the correct explanation of A. 4. A is correct, but R is not correct. The assertion is, in a particular point defect, an ionic solid is electrically neutral, even if few of its cations are missing from its unit cell. That is a correct statement. Now, in an ionic solid, frontal defect arises due to dislocation of cation from its lattice site to interstitial sites, maintaining overall electrical neutrality. This also is correct. But the reason does not explain the assertion. So therefore the option must be 3. Since cations are dislocated into interstitial sites, electrical neutrality is maintained in frontal defect. In metal deficiency defect also electrical neutrality is maintained where a nearby metal ion acquires a higher positive charge. Question 13. Slight yellow color of sodium chloride crystal when heated in an atmosphere of sodium is due to option 1, vacancy defect, interstitial defect, metal excess defect, metal deficiency defect. When alkali metal halide is heated in an atmosphere of metal vapor, metal atoms get deposited on the surface of the crystal. The halide ions diffuse to the surface, combine with the metal atom to form metal halide. This causes metal excess defect. The electron moved from the metal atom on the surface diffuse into the crystal and occupy the anionic site. The anionic site occupied by unpaired electron is called ascendus. Such crystals show color due to excitation of electrons under visible light. Sodium chloride show yellow, lithium chloride shows pink, and potassium chloride shows lilac or violet color. So the answer is metal excess defect. An excess of potassium ion makes potassium chloride crystal appear violet or lilac in color, since option A, some of the cationic sites are occupied by an unpaired electron. Some of the anionic sites are occupied by a pair of electrons. There are vacancies at some anionic sites. F centers are created which impart color to the crystal. So the color is due to the formation of F centers where the anionic sites are occupied by unpaired electrons. Question 15. Match the type of defects given in column 1 with the statements given in column 2. Column 1, column 2, impurity defect, metal excess defect, metal deficiency defect. Column 2, sodium chloride with anionic sites called F centers. FeO with the Fe3 plus, sodium chloride with the strontium. This defect occurs when metal shows variable valency. Option 1, option 2, option 3, and option 4. Column 1, first is impurity defect. So impurity defect F centers, sodium chloride with the strontium 2 plus ions. So strontium in sodium chloride is an impurity. So therefore we can connect 1 to C. 1 to C. Then metal excess defect. That is, when sodium chloride is heated with in an atmosphere of sodium, some of the chloride ions migrate to the surface, causing vacancy. So the vacancies are occupied by unpaired electrons and that forms F centers. But at the same time, the number of sodium ions increases. So therefore, this is a metal excess defect. So we can connect 2 to A. Next is metal deficiency defect. So FeO with Fe3 plus. That means this is a metal deficient compound. So we can connect this to this one. And this defect occurs when metal shows variable valence. So metal deficiency defect also occurs due to option D also. So therefore the correct answer should be option 4. Which type of solid will conduct heat and electricity? 1 ionic solid, 2 covalent solid, 3 metallic solid, 4 molecular solids. So only metallic solids will conduct heat and electricity. Question 17. The impurity to be added to silicon to get an N-type semiconductor, the number of valence electrons required in the impurity is 1, option 2, 2, option 3, 4, option 4, 5. So silicon, the valency of silicon is 4. So in order to get an N-type, the impurity should have a valency of 5. Germanium can be converted to a p-type semiconductor by doping with dash impurity, trivalent, tetravalent, pentavalent, divalent. Germanium has 4 valency, so if we dope it with a trivalent element, that will show a p-type semiconductor. From ionic radius ratio of a crystal, we can know about which of the following. 1. Magnetic property, nature of chemical bond, type of defect, geometrical shape of crystal. So from ionic ratio we get a clue of the geometrical shape of the crystal. Radius ratio means radius of cation by radius of anion. So from this radius ratio we mainly get a clue about the structure of the compound. When germanium metal is doped with a little of indium or gallium, one gets 1 p-type semiconductor, n-type semiconductor, insulator, For rectifier, germanium is group 14. Indium and gallium are group 13 elements. So therefore we will get a p-type semiconductor. Which of the following oxide behaves as conductor or insulator depending on temperature? Titanium oxide, SiO2, TiO3, magnesium oxide. There are some oxides which behave as conductor or insulator depending on temperature. Some examples are vanadium oxide, vanadium dioxide, trioxide, titanium trioxide, etc. So the answer is titanium trioxide. Choose the incorrect statement from the following. Option 1. Germanium doped with phosphorus will be an N-type semiconductor. Transistors are made by sandwiching one type of semiconductor between layers of another type of semiconductors. Indium antimonide is 1216 compound semiconductor. VO3 shows metallic or insulating properties depending on temperature. Germanium doped with phosphorus will be an N-type semiconductor. That is correct. We have to choose the incorrect statements. And option 2 also is correct. Now come to option 3. Indium antimonide is a 1216 compound. That is wrong. So this is the answer. Indium comes under group 13 and antimony comes under group 15. Therefore, indium antimonide is a 1315 compound semiconductor. Question 23. Which of the following compounds will be repelled when placed in an external magnetic field? 1. Na2COCl4. These are complexes. K3FeCN6. K3COF6. Diamagnetic substances are weakly repelled by a magnetic field. In such compounds, all the electrons will be paired. So we have to check the electron configuration of these central atoms in these complexes. So first one is Na2CuCl4. The complex ion is CuCl4 minus. So copper is in the +2 oxidation state. So the electron configuration will be 3d9 4s0. So therefore one unpaired electron is there. So it should be paramagnetic. Second compound is cadmium chloride, CdCl4 minus, Cd2 plus, and Cd2 plus is 4d10. So all the electrons are paired, so it should be diamagnetic. Now we can check this also. K3FeCN6, that is FeCN6 thrice, and Fe3 plus. And in Fe3 plus, it is 4d5. So it contains one unpaired electron, so that should also be paramagnetic. Then K3 is COF6, that is COF6, that is cobalt 3 plus, and F4d6. Since fluorine is a weak ligand, this will be a high spin complex. So this also is paramagnetic. So the answer is second option. In which of the following all the dipole moments are permanently aligned in the same direction when placed in an external magnetic field? Diamagnetic, paramagnetic, ferromagnetic, antiferromagnetic. So that is ferromagnetic. Ferromagnetic materials are used for preparing permanent magnets. Which of the following substances possess antiferromagnetic property? CrO2, Fe3O4, H2O, MnO. MnO shows antiferromagnetic property. Which of the following statements is not true? 1. Paramagnetic substances are weakly attracted by magnetic field. Ferromagnetic substances cannot be magnetized permanently. The domains in antiferromagnetic substances are oppositely oriented with respect to each other. Pairing of electrons cancel their magnetic moment in diamagnetic substances. Paramagnetic substances are weakly attracted by the magnetic field. So we have to find out the incorrect statement. Ferromagnetic substances cannot be magnetized permanently. Ferromagnetic substances are used for making permanent magnets. So option 2 is the correct one. That is an incorrect statement. Which of the following oxides show electrical properties like metals? 1. Chromium oxide, silicon dioxide, sulfur dioxide solid, magnesium oxide. That is CrO2. Question 28 is a paragraph type question. So read the following paragraph and answer the question given below. Based on magnetic properties, substances can be classified into different types. 1. Paramagnetic substances. These are weakly attracted by the magnetic field. They are magnetized in the same direction as that of the external magnetic field and lose magnetism in the absence of field. They possess one or more unpaired electrons. 2. Diamagnetic substances. Weakly repelled by magnetic field. Weakly magnetized in the magnetic field in the opposite direction. All electrons are paired. 3. Ferromagnetic substances. Attracted very strongly to the magnetic field. Can be permanently magnetized. Metal ions are grouped to form domains, and these domains orient in the same direction as that of magnetic field. Orientation persists even when magnetic field is removed. Examples are iron, cobalt, nickel, CrO3, etc. For antiferromagnetic substances, they form domains like ferromagnetic substance. No net magnetic moment as the domain orient opposite direction in the magnetic field. MnO, CrO2O3, Fe2O3, etc. Ferrimagnetic substances weakly attracted to the magnetic field compared to ferromagnetic substances shows domain structure, but with the domains the spins are arranged parallel and antiparallel direction in unequal numbers. They lose magnetism on heating and become paramagnetic. Examples are Fe3O4 and certain ferrites. 1. Which of the following statements is not true? 1. Paramagnetic substances are weakly attracted by magnetic field. Ferromagnetic substances cannot be magnetized permanently. The domains in antiferromagnetic substances are oppositely oriented with respect to each other. Pairing of electrons cancel the magnetic moment in the diamagnetic substances. So option 2 is not true. Ferromagnetic substances cannot be magnetized permanently. So ferromagnetic substances are used for the preparation of permanent magnets. Option 2. A ferromagnetic substance becomes permanent magnet when it is placed in a magnetic field because all the domains get oriented in the direction of magnetic field. All the domains get oriented in the direction opposite to the magnetic field. Domains get oriented randomly. Domains are not affected by magnetic field. So option 1 is the correct one. Which of the following compounds show antiferromagnetism? 1. Magnetite, 2. CrO2, 3. Hematite, 4. MgF2O4. And answer is hematite. Hematite is Fe2O3. Then 4 permanent magnets are made of 1. Paramagnetic substances, antiferromagnetic substances, ferrimagnetic substances, and ferromagnetic substances. Permanent magnets are made of ferromagnetic substances. Match the type of magnetism with the corresponding characteristics. Paramagnetic, diamagnetic, ferromagnetic, antiferromagnetic, ferrimagnetic. These are the characteristics given. Option 1, option 2, option 3, option 4. So first paramagnetic. So paramagnetic must contain unpaired electrons. So we can connect A to 2. Then diamagnetic substance. These are weakly magnetized in the field in the opposite direction. That is why they are repelled by the magnetic field. Now, ferromagnetic substances. And in ferromagnetic substances, the spin orientations are retained even when magnetic field is removed. Now, antiferromagnetic and in antiferromagnetic domains are oppositely oriented in the magnetic field. For ferrimagnetic, magnetite is an example. Therefore, the correct option is option 4.